So here we will take up another problem on resultant of non-concurrent force system. It's a practical problem. So this is civil engineering construction. It's a civil engineering structure, a dam. This is a dam. So cross section of that. A typical cross section of a dam is like this. Here on this side we have the reservoir. This is called as the reservoir where water is stored. So due to that storage of water, a pressure will be exerted on the wall of the dam. That pressure is given here as 50 kN in form of pressure force. And you have the weight of the dam acting at the center of gravity of the dam, which is 120 kN. It acts downwards. This is called as hydrostatic pressure force, which acts perpendicular to the wall of the dam. And this is weight of the dam, which acts vertically downwards. And there is one more force here. This is nothing but the weight of water which is stored on this side. It is 30 kN on the downstream side. This is called as upstream side, and this is called as downstream side. So water flows from upstream to downstream side when the gates are opened. Now that means there are three forces acting on this cross section of the dam: 50 kN horizontal, 120 kN vertical, and 30 kN incline, but making an angle 90 degrees with the downstream face. This is called as the downstream face of the dam, and this angle is 60 degrees what he has given. And the base width of the dam, AB is called as the base width of the dam, which is taken as 6 meters. It is a small dam. Maybe other dam we can take. So you can say other dam is made of soil. So the question is determine the resultant of the forces acting on a dam as shown in the figure. Check whether the dam is safe or not. So first we will find out the resultant, both in magnitude, direction, as well as we will locate the position of the resultant. Then we will check whether the dam is safe or not. So I will just tell you the condition for which the dam should be safe. First let us do the resultant calculation. So as usual we have to calculate sigma fx, taking forces acting towards side positive, sigma fy, taking upward forces positive. Now here there are only three forces: 50 kN, 120 kN, 30 kN. So to write this, we have to resolve this 30 kN force. If we resolve this 30 kN force, you can see here, if I draw a horizontal here, since this is 60 degrees, this will be 60 degrees. When this is 60, this is 90, so this will be 30. Naturally, because total should be 180. So when this is 60, this is 90, this should be 30 degrees. That means if you resolve this force, 30 kN force into two components like this, so the horizontal component will be like this, vertical component will be like this. This angle is 30 degrees. This is 30 cos 30 degree. This will be 30 sin 30 degree. So all this you should do. And if these two forces you need to resolve because one is horizontal and one is vertical. Now let us apply sigma fx here. Forces acting towards right positive, this 50 kN is positive, and here this 30 cos 30 is negative because it is acting towards left. So 50 minus 30 cos 30. So that is the value of sigma fx. Sigma fy will be upward positive, downward negative. So this is minus 120 and this is also minus. So both are minus. Minus 120 minus 30 sin 30. So if you simplify this, you will get the values of sigma fx and sigma fy. So in this case, sigma fx is 50 minus 30 cos 30. So 30 into cos 30. So it works out to be 24.019 24.02 kilonewton. Please do that. This is positive, that means it is acting towards right. Then sigma fy, both are negative. So 120 plus 30 sin 30 is 15. So that means it is 135, but negative. So minus 135 kilonewton downwards. Now once you know the directions of sigma fx and sigma fy, you can just find the direction of the resultant force. So sigma fx is like this, sigma fy is like this. Definitely resultant force lies in the fourth quadrant. So depending on the direction of sigma fx and sigma fy, you can decide the direction of the resultant fourth quadrant. Now alpha we will find out. So magnitude and direction we need now. So magnitude of R resultant force, magnitude of resultant resultant force R is equal to sigma Fx square plus sigma Fy square under root, so which comes out to be root of 24.02 square plus minus 135 square. So let us simplify this. 135 square plus 24.02 square, so which comes out to be, so 137.12 kilonewton, that is the magnitude. Of course, the direction alpha, direction of R is equal to alpha, that is tan inverse of modulus sigma Fy by sigma Fx, which comes out to be tan inverse of, so minus 135 by 24.02. Since we are getting modulus, it becomes positive. So the answer will be tan inverse of 135 divided by 24.02, which comes out to be 79.9 degrees. 79.9 degrees. So these two are the magnitude and direction of the resultant force. Now let us find out the position of the resultant with respect to any of the points. I will take with respect to this point A. So let us calculate position of R or location of R with respect to point A. So when you are finding the position of R with respect to point A, we need to calculate sigma NA by taking clockwise moments positive. So sigma NA is equal to, we will now write the moments of all the forces about the point A. So here we should be very careful about this point where about this force, 30 cos 60 and 30 sin 60 force. When you first time write this, due to this 50 kN force, it is giving a clockwise moment about A. So plus 50 into 3. So plus 50 into 3, clockwise is positive. Then due to this 120 kN it is acting at a distance of 2 meter. So it will be, this is also clockwise, 120 into 2. So plus 120 into 2. Now coming to the this force, there are two forces here. Now you should be careful. This force, this horizontal force, if you extend this, horizontal force is this, vertical force is this, components of these two. If you extend this horizontal force, which is 30 cos 30, this 30 cos 30 is giving an anti-clockwise moment about A. So minus 30 cos 30 into distance is this distance. Distance is this vertical distance. So this is where you should be very careful. So this vertical distance we have to calculate now, because he has given the inclined distance 1 meter and this angle is known. So let us calculate this distance by taking the triangle. So this small exercise we have to do. We have to take the sine ratio and cos ratio and we have to get the values. Now just what I will do here is, so this is C, point C, this is B, and let me take this as a point D. Now I consider this CDB, triangle CDB, like this. This triangle I will take now CDB, where this is 60 degrees and this is 1 meter. This is 1 meter. Now I need these two distances. By taking the sine ratio and cos ratio, we can find out these two distances. So sine 60 will be opposite by hypotenuse, that is CD by 1 meter, or CD is equal to sine 60. So sine 60 is 0.866 I think. So sine 60 is equal to 0.866 meter. Okay, so CD value is 0.866 meter. Similarly, if you take cos ratio, cos 60 is adjacent by hypotenuse, that is BD by 1 meter. So BD is equal to cos 60 is half, that is 0.5. So this is 0.5. Now we got the values CD and DB. So this value is 0.866, whereas this value is 0.5. Now let us calculate the moments due to these two forces. Now this 30 cos 30, as already told, it is giving an anti-clockwise moment about A, and the distance is this vertical distance, which is 0.866. we should be very careful about the distances. Now, due to this vertical force, this force 30 sin 30 force, this is acting here. So draw, explain this line of action. So this distance I have to take from A to this point, AD. AD I have to take. That is the distance where this 30 sin 30 force is acting. So this AD will be 6 minus 0.5. Okay, because DV is 0.5, so you have to deduct that. So 6 minus 0.5 is 5.5. So that means it is giving a clockwise moment. So plus 30 sin 30 into 5.5, 6 minus 0.5. So this is the algebraic sum of the forces about the point A. So I have considered this force, and these two forces. Now if you simplify this, 50 into 3 is 150 plus 120 into 2 is 240 is equal to 390 minus 30 into cos 30 into 0.866. Then plus 30 into sin 30 is 15 into 5.5. So the value is 450 kilonewton meter. So it is giving clockwise, it is positive, therefore the moment is clockwise. Now we will calculate the distance where that resultant force is acting from the point A. So for calculating the perpendicular distance, D is equal to sigma MA by R. So which is 450 divided by 137.12. 450 divided by 137.12. It comes out to be 450 divided by 137.12, which is 3.28 meters. So this is the perpendicular distance of the line of action of the resultant force from the point A. Now I need to calculate x-intercept, that is the distance of the resultant from the point A, which is given by d by sin theta, sin alpha. So d is 3.28 divided by sin of alpha is 79.9 degrees, so which comes out to be, so 3.28 divided by sin 79.9 degree, which is 3.33 meters. 3.33 meters from A. So the x-intercept is 3.33 meters. That means the meaning of that is this is the dam. So this width of the base width of the dam is 6 meters. 6 meters. This is point A. This is B. Now, since this is 60 degrees, of course, we have given. Now the resultant lies in the fourth quadrant. You can see here. That means the resultant is acting something like this. This is off because this should give a clockwise moment about A. See here. So it should be like this. It cannot be here. If the resultant is here, then it gives an anti-clockwise moment. So therefore, resultant should be here. This value is your x value. So this x is 3.33 meters. That's what we have got. Just slightly better than this midpoint. Now we have to check whether the dam is safe or not. So this is alpha. So one condition is there in the design of dams. So the condition is the dam is safe if and only if IFF, the resultant, that is resultant force R, passes through middle third of the base. This is very important condition. Middle third of the base. You have to understand this wording. What do you mean by middle third? So here the base is AB, which is 6 meters. See here. Base is AB, 6 meters. This should be divided into 3 divisions. 3 divisions. 1, 2, 3. So each division is 2 meters, 2 meters, 2 meters. 3 equal divisions. Now the dam is safe if the resultant passes through the middle third. So middle third is this portion. Middle third is this portion. So you have to check whether the resultant passes through that middle third. So you have the value of x as 3.33. So 3.33 will be 3 meters will be exact center. 3.33 means somewhere here. So x is this. This is the x value, which is nothing but 3.33 meter. Now you can see that if you plot that, so the middle third varies from 2 to 4. That means if the x value in this case, if it is between 2 to 4 meters, then it is safe. So here we have got 3.33 meter. Therefore, that resultant passes through here. You can see here this resultant passes through the middle third. Therefore, the dam is safe. This is alpha. This is r. This distance, x-intercept distance, if it lies between 2 and 4, because the base width is 6 meters, middle third dimension vary from 2 meters to 4 meters. In this case, x value is 3.33 meter. So this is between 2 to 4 meter. Therefore, it is safe. Here in this case, x is equal to 3.33 meter. Therefore, the resultant R passes through middle third of base. Therefore, dam is safe. So this is how they can. This is a practical problem. So wherein he will give the forces acting on a dam. Of course, it's a very simple dam, urban dam. Normally, in dams you have different types. Gravity dam, it will be having huge heights. So whereas this is a small urban dam where the base width given is 6 meters and only 3 forces are given. One is water force, another is self-weight, another one is the water on the weight of water on the other side. So by giving 3 forces, we have calculated the resultant, and we have to find the x-intercept of the resultant. If the x-intercept of the resultant falls in the middle third of the base, then we can say the dam is safe. In this case, the resultant should pass through in between 2 and 4 meters. Of course, here x value we have got 3.33 meter, which lies in between 2 and 4. Therefore, the dam is safe.